We've grown accustomed to this route, buying a ticket, a soft seat in the car, a cup of coffee on the fold-down table, 35 minutes of monotonous hum outside the window, and you're in another country. It feels like a mundane subway ride, where the ocean overhead is nothing more than an abstract fact. But this comfort is a carefully staged lie. If you press your palm against the glass, you can feel a barely perceptible vibration of resistance. Right now, millions of tons of salt water are pressing against the arches with a single goal: to crush them.
The entire system hangs by an invisible yet constantly tested breaking point.
A cracking chalk layer, flooded drill shields, temperatures nearing 40 degrees and the deafening roar of metal cutters, financial bankruptcies, investor panic, and the threat of a complete rock collapse right at the start. This tunnel is neither a transport artery nor a triumph of European unity. It is an artificial cavity within a geological fault, requiring constant technical intervention. It is a concrete throat forcibly inserted into the body of the English Channel. It functions in defiance of the laws of physics and hydrodynamics, consuming colossal amounts of energy. By the end of this story, it will become clear that the English Channel was never conquered. Engineers did not subdue the strait, but merely leased a narrow passage from it in exchange for massive expenditures.
We will understand why this complex structure will never become truly self-sustaining.
Its outward stability is paid for by daily invisible labor. Let's go back to the beginning, to an era when there was neither high-strength concrete nor laser positioning. There was only icy water, gray cliffs, and an island whose safety depended on absolute isolation. To the moment when the first person looked at the stormy waves and decided to carve a path beneath them. Britain survived in world history only thanks to water. The English Channel was an impassable moat that shattered the Spanish armadas and halted the armies of the continent. More than 30 kilometers of stormy sea worked better than any fortress walls. Water was the absolute physical guarantor of the crown's sovereignty. The idea of building a land bridge seemed not just madness, but treason. Isolation had shaped the nation's psychology for centuries.
No one wanted to voluntarily open the door to a fortress that was technically impossible to besiege.
Geography dictated military doctrine with no room for compromise. The first tunnel designs were drawn up as early as the beginning of the 19th century. French engineer Albert Mathieu proposed digging a road under the seabed for horse-drawn carriages. He even sketched an artificial island in the middle of the strait for changing tired horses. The project looked elegant on paper but had no connection to the material reality of the time. The British Admiralty viewed these plans with growing horror. To the generals, any tunnel represented a pre-dug trench for enemy soldiers. The fear of a sudden invasion from underground paralyzed any attempts to begin surveys. For many years, engineering became a hostage to military paranoia. The post-war world began to change, but political stereotypes broke down slowly. Drilling technologies improved, allowing mountains to be bored through in the Swiss Alps.
But the strait remained untouched, like a sacred zone of alienation between two worlds.
The fear of invasion still outweighed any economic benefit from connecting the systems. It was not until the mid-1950s that logistics began to dictate its terms. The old port infrastructure was choking under the growing volume of road and rail freight. The economy demanded a constant pace that water simply could not physically provide. Isolation began to kill the island more slowly but surely than any foreign army. The transport blockade was becoming too costly for the British economy. Ferries were critically dependent on the weather, goods were rotting in warehouses, and trade growth was slowing. The authorities had to admit that the country could no longer survive cut off from continental markets. The main enemy was now logistical inefficiency, not some abstract land-based threat. A radical political decision was needed to break the centuries-old tradition of isolation. Margaret Thatcher and François Mitterrand shook hands, launching a historic process of rapprochement. It was an alliance of hard-nosed pragmatists who understood the mathematical inevitability of integrating infrastructure. But they set one brutal condition that defined the entire subsequent architecture of the crisis. Engineers had to abandon the idea of a road tunnel for good due to the laws of physics. The threat of thousands of people being poisoned by exhaust fumes required fantastical cross-ventilation systems. The most complex, yet the only viable concept, A sealed capsule was chosen.
The tunnel was to be exclusively for rail traffic, isolated from internal combustion engines.
The design became extremely complex. Instead of a single main line, it was decided to excavate 3 parallel tubes at once. 2 were intended for high-speed trains, and the third, central one, for maintenance. This tripled the volume of rock excavation and pushed the scale beyond standard calculations. The project ceased to be merely a road, transforming into an unprecedented underground labyrinth. A massive mobilization of heavy equipment and personnel began on the shores of both countries. Huge construction consortia emerged, creating temporary megastructures for the sake of survival. Competitors became partners to share the unbearable burden of capital expenditures. Blueprints turned into reinforced concrete at a frightening, almost frantic pace. Thousands of workers began flocking to the coastal areas of Kent in Britain and Pas-de-Calais in France. Giant workers' camps, dedicated concrete plants, and transportation hubs were erected. The coastal landscape was forever altered, covered by a network of temporary access roads.
The construction machine had been set in motion and could no longer be stopped without catastrophic losses.
The system was preparing to plunge into a hostile environment that would not forgive the slightest weakness. An inevitable collision was looming between financial pressure, deadlines, and the indifferent geology of the ocean. The project had reached the point of no return. The drill heads were positioned in their launch shafts, awaiting the command to plunge into the darkness. The entry point for the machines beneath the seabed was determined by strict geological conditions, not by the architect's wishes. Beneath the strait lies a layer of blue Cretaceous marl clay about 30 meters thick. This is a dense, impermeable structure, theoretically ideal for the operation of heavy rotary machinery. The main engineering challenge was to keep the machines strictly within this narrow layer. If the tunneling shield moves even a meter higher, it will break through the ceiling of safe clay. In that case, the ocean, under monstrous pressure, will rush directly into the working face.
If the drill drops lower, the machine will become firmly stuck in unstable, loose sandstone.
The space for vertical maneuvering of the multi-ton machines was mathematically microscopic. The pressure of the rock mass on the outer hull increased with every meter of descent. It constantly tested the strength of the hydraulic seals and the operator's nerves. The men found themselves trapped in cramped metal cylinders beneath a colossal layer of cold water. The psychological strain of realizing this fact was no less devastating than physical exhaustion. Every new meter of progress came at the cost of cutters ground to powder and burnt-out electric motors. The mechanisms began to experience overloads that no civilian component was designed to withstand. The noise from the cutting rotor reached a level that physically destroyed the hearing. Constant vibration crumbled the rock around them and loosened the bolted joints inside the shield. Speaking at the face was impossible. Commands were given exclusively through hand signals and light signals. Dust and machine oil vapors hung in the air as a thick, suspended mist that refused to settle. We had to breathe through bulky respirators, whose filters became clogged with sticky mud within a couple of hours. It was an industrial purgatory, hidden deep beneath the smooth surface of the strait. Drilling speed remained the main measure of success for the nervous investors on the surface. Every minute of unexpected downtime translated into millions in penalties for the builders. Management demanded that the cutting pace be ramped up, completely ignoring warnings about system overheating.
The equipment was pushed to the limits of its rated capacity, risking a breakdown.
The incursion into the depths of the English Channel had ceased to be an elegant engineering problem from the textbooks. It had degenerated into a brutal, exhausting battle of steel against unpredictable rock. None of the workers knew for sure what awaited the rotor just beyond the next meter of excavation, and the ocean above continued to press down silently with its dead, absolute mass. The French team faced a massive natural disaster almost immediately after starting. Their offshore section turned out to be a geological nightmare, densely riddled with vertical microcracks. Seawater under pressure of several atmospheres began to force its way through the rock directly into the borehole. The dense chalk instantly turned into a sticky, corrosive paste that completely jammed the mechanisms. The drilling rigs, designed by engineers for dry rock, began to choke on the slurry. Water flooded the high-voltage equipment, causing constant short circuits in the confined space. Workers stood knee-deep in skin-corrosive, salty mud, trying to clear the conveyors by hand. The tunneling rate dropped to critical levels, threatening to bring the international project to a permanent halt. Both groups of tunnelers realized that the rock wasn't going to give way without a fight. The illusion of a quick and efficient journey through a soft layer of clay was shattered by the physics of the soil. Each kilometer of tunnel began to cost the consortium 3 times as much as the originally approved budget. The system began to devour credit resources at an alarming, uncontrollable rate. Management had to radically revise shift schedules and the logistics of soil removal. The mine cars shuttling between the face and the surface could not handle the volume of wet rock. Mud clung to the wheel sets, causing derailments inside the narrow service tunnels. Every accident on the spoil disposal line paralyzed the main rotor's operation. The pressure from creditors on management became unbearable, demanding results at any cost. Engineers were forced to cut corners, simplifying protocols to save time. Risk became an everyday routine, and safety took a back seat in the face of default. The project teetered on a fine line between spectacular success and total financial collapse. The people on the front lines were working at the limits of the human body's biological capabilities. Dehydration, constant micro-traumas from flying debris, and chronic sleep deprivation became the norm. Medical stations on the surface received dozens of workers every day suffering from exhaustion and pulmonary spasms. The facility was mercilessly consuming the health of those who built it. This was the moment when the masks were finally torn away from the original plan. The idea that modern technology could easily subdue nature turned out to be a naive and costly mistake. The Earth dictated its own terms, forcing people to adapt to the chaos of geological faults. The tunnel survived only through a constant infusion of money and human sweat. A tunnel boring machine is not just a drill, it is a moving underground steel mill. It is longer than 2 full-size football fields, and its mass reaches thousands of tons of iron. On board, dozens of engineers work, eat, and make decisions in a continuous cycle. It is an autonomous steel parasite, digesting rock and leaving behind smooth concrete. The rotating rotor disc bit into the monolith, cutting away tons of compacted soil every second. A system of conveyor belts instantly picked up and flung this mass backward toward the waiting rail cars. At the same time, massive hydraulic arms precisely installed heavy reinforced concrete segments of the protective ring. The tunnel itself was physically assembled behind the machine, creating a continuous barrier against external pressure. Inside this enclosed complex, the heat from dozens of running oil pumps was unbearable. The standard cooling systems couldn't handle the heat dissipation in the sealed stone chamber. The temperature regularly exceeded 40 degrees Celsius, accompanied by unnaturally high, almost tropical humidity. People stood at the control panels in nothing but shorts, drenched in sweat and gasping for clean oxygen. There, facing the bare rock, they worked under artificially created high atmospheric pressure. This was done to prevent water from flooding the compartment during part replacement. The procedure was deadly dangerous and required subsequent prolonged decompression, just like for divers. The slightest mistake with the pressure valves could lead to decompression, sickness, or an explosive flood. The shield's life support infrastructure stretched for kilometers behind it. Ventilation pipes, power cables as thick as a hand, and water lines grew longer every day. The farther the complex moved from the shore, the more difficult it became to supply it with power. A drop in voltage could cause the cooling pumps to shut down and lead to disaster. The machine and the people inside it became a single symbiotic organism, isolated from the outside world. Shifts lasted 12 hours, after which the workers emerged to the surface, completely exhausted. Returning to the light was accompanied by temporary disorientation and a ringing in the ears that wouldn't subside for days. The tunnel methodically drained the strength from everyone who touched its steel lining. The very nature of this process precluded any weakness or attempt to fully automate the labor. The human factor remained the glue that held this cumbersome system from falling apart. Only the hands of the mechanics and welders could repair leaks in the hydraulics in time. The gigantic mechanisms turned out to be completely dependent on the endurance of the fragile human body. The most daunting mathematical problem of the entire decade was the precise alignment of the two directions. The British and French drills were supposed to meet exactly in the middle of the strait, deep within the solid rock. A navigational error of even a few dozen centimeters would have meant the project's fatal failure. It was physically impossible to rework the curved joint of concrete rings at a depth of 50 meters below the seabed. Traditional methods of surveying and orientation underground were completely ineffective here. The use of magnetic compasses was strictly prohibited due to the massive amounts of iron in the tunnel boring machine structures. Satellite navigation signals cannot penetrate millions of tons of water and rock. The engineers had to rely exclusively on highly sophisticated laser theodolites and aviation gyroscopes. When there were 100 meters left to the meeting point, the large rotary shields were forcibly stopped. Further drilling by the machines could have led to an unpredictable collapse of the weakened partition. The massive steel drill heads were permanently buried in special side tunnels and filled with concrete. Workers broke through the final few dozen meters by hand, using only pneumatic jackhammers. The historic meeting took place on December 1st in the narrow Central Service Tunnel. A British tunnel worker broke through the last stone lintel and widened the opening with a crowbar. Through the hole that had formed in a cloud of dust, he saw the bright light of French halogen lamps. The navigational misalignment along the axes of the enormous pipes was only 35 centimeters. It was an absolute engineering triumph, instantly obscuring the entire monstrous underside of the process. Journalists on the surface were treated to the perfect image of two nations shaking hands deep underwater. Champagne flowed freely, and politicians delivered rousing speeches about the triumph of reason over the elements. But for the engineers, this breakthrough was only the beginning of a whole new phase of challenges. The meeting marked the end of drilling, but not the end of physical testing for the entire structure. Now the task was to connect the systems of two completely different technological schools into a single chain. British metric systems and French standards had to be integrated into a single working unit without any gaps. A failure at the interface between the systems threatened a short circuit on a line carrying tens of thousands of volts. The system closed, forming a single open wound in the body of the geological formation. The euphoria quickly evaporated when it became clear that the bare tunnel was not yet a transport artery. The hole that had been drilled had to be immediately transformed into a sealed life support system. There was no time left for celebration as the financial meter kept ticking. The tunnel that had been bored through was nothing more than a damp, dusty concrete shell. The task ahead was to transform 3 empty cold tubes into the most complex transportation system in European history. The non-stop laying of hundreds of kilometers of heavy rails, power cables, and cooling lines began. The artificial structure began to be overgrown with copper nerves and steel blood vessels. Engineers designed special shuttle trains capable of transporting passenger cars and long-haul freight trucks. Their dimensions were strictly dictated by the inner diameter of the concrete ring, leaving minimal aerodynamic clearances. The locomotives were equipped with triple redundant braking systems in case of sudden failure en route. The aerodynamics of the cars had to withstand the colossal pressure of the compressing air in the closed tube. To combat the destructive piston effect, special relief shafts were cut between the tracks. When a train weighing thousands of tons races at tremendous speed, it pushes a dense wall of air ahead of it. Without relief valves, this pressure would have torn apart the car bodies or destroyed the concrete arches. The tunnel was literally taught to breathe, diverting excess atmospheric pressure into an adjacent service tunnel. Tickets had to be sold at triple the price just to cover the interest on the colossal loans. Ferries suddenly responded with price dumping, launching an aggressive price war for every cargo carrier. The tunnel entered service not as a monopolist, but as a bankrupt entity desperately struggling to survive. The commercial illusion of easy money evaporated upon colliding with the harsh reality of the market. Queen Elizabeth and President Mitterrand ceremoniously cut the red ribbon in May 1994. The television footage radiated confidence, progress, and faith in the boundless possibilities of a united Europe. No one on the podium mentioned that the system was originally designed at the limits of its physical and financial capabilities. The news tickers remained silent about the fact that every trip was working to pay off astronomical debts. The tunnel began its commercial life burdened by an unbearable, almost fatal weight of expectations. It had to operate flawlessly every second to avoid panic among investors and passengers. Any train delay caused by a sensor malfunction instantly sent the company's stock plummeting on the exchange. The system entered a state of constant stress that would never end. The illusion of conquered depths was successfully sold to the mass consumer through advertising brochures. People believed that descending 50 meters below the ocean floor was as safe as getting on a bus. But engineers in the control centers knew the price of this outward perfection. They understood that the mechanism would function normally only until the first serious internal spark. The true test of its structural integrity came during the cool autumn of 1996. A heavy freight train carrying heavy-duty trucks caught fire due to a short circuit while it was still moving. The wind rushing through the narrow tunnel at hurricane-force speeds instantly turned the localized flames into a catastrophe. Within minutes, the steel transport capsule turned into a giant horizontal aerodynamic furnace. The temperature inside the enclosed space quickly surpassed 1,000 degrees Celsius. Under such extreme heat, high-strength concrete begins to literally explode and break off in chunks, exposing the rebar. The ocean overhead ceased to be an abstraction. The thinned, overheated arch could burst under pressure at any moment. The standard water-based fire suppression system was overwhelmed and could not cope with such a thermal load per square meter. The engineer kept his cool, stopped the train, and led the people through the airtight doors into the service tunnel. This narrow central escape shaft, built by engineers many years ago, fully justified the colossal expense. The people survived, isolated from the smoke, but the main tunnel itself sustained critical structural damage. The fire raged unchecked for several hours, burning kilometers of communication cables to ashes and melting the steel rails. Restoring the burned-out section required many months of manual labor and massive new financial investments. The concrete had to be cut away and poured anew, restoring the protective ring to its original thickness. Stricter response protocols and ultra-powerful fire suppression systems were urgently developed and implemented. The tunnel was physically saved, but the price of that salvation was an irreversible loss of public trust. What happened proved that the greatest threat comes not from the ocean outside, but from the contents inside. Trucks carrying fuel and goods became a ticking time bomb, constantly moving beneath the strait. Every new voyage carried the possibility of a repeat of the scenario, which could not be completely ruled out. Engineers realized that the risk had shifted from the realm of the hypothetical to that of the statistically inevitable. Insurance companies drove terminal service rates up to astronomical heights. Shareholders once again found themselves on the brink of financial ruin, calculating the losses from the line's downtime. The project, which was supposed to be a symbol of stability, had become a chronic headache. Confidence gave way to tense anticipation of another failure in the overloaded electronics. The trial by fire changed the very philosophy of operating this transport corridor. The authorities and the operating company stopped treating it as an ordinary railway. It was reclassified as a high-risk facility requiring military-level monitoring. The carefree attitude of the early years burned up along with the rail cars in 1996. The following years turned the tunnel into an exhausted hostage to its own economic importance. Daily traffic volumes grew exponentially, quickly exceeding even the most optimistic forecasts of its creators. Millions of tons of cargo and tens of millions of passengers rushed through this narrow bottleneck under the strait every year. The infrastructure wore out much faster than the safety specifications had anticipated. The damp, salt-laden sea air sucked in by the trains triggered accelerated metal corrosion. The heavy steel rails had to be replaced with alarming regularity due to the micro-cracks developing within them. Powerful drainage stations operated non-stop, aggressively pumping out thousands of liters of groundwater. The tunnel required constant, round-the-clock maintenance in real time. Every maintenance window for nighttime repairs reduced profits and caused dissatisfaction among carriers. But metal fatigue could not be ignored. The system did not forgive even the slightest negligence. Dispatchers balanced the logistical demands of running trains more frequently against the need to preserve the tracks. This fine line of compromise between speed and risk became the main daily routine. In 2008, a second major fire occurred, serving as a brutal reminder of the limits of physical durability. The scenario repeated itself almost exactly, despite all the new sensors and early warning systems. A freight train caught fire again, and once more the concrete began to flake off under the influence of extreme temperatures. No human casualties were reported, but the trend had become a frightening pattern. Each such serious incident instantly paralyzed the logistics of two countries at once. Traffic stoppages caused multi-million-dollar losses to businesses on both sides of the English Channel. The tunnel proved to be too narrow and vulnerable a point for a continental-scale economy. The total dependence of entire industries on this single link became a strategic threat to all of Europe. Added to the pressures of nature and technology was the uncontrollable political factor of migration. Thousands of refugees tried to break through the tunnel on foot, jumping onto moving platforms. This led to tragic deaths on the tracks and forced complete stoppages of traffic. The facility, created to unite economies, became an arena of conflict between desperation and the law. The infrastructure had finally lost its original romantic aura of progress. It had become a heavy burden, a complex organism that was constantly ill and required expensive medicine. The illusion of durability gave way to an understanding of the structure's absolute systemic fragility. The bridge beneath the water proved far more capricious than any sea above it. Today, the Eurotunnel is a heavily guarded, restricted access facility with unprecedented security measures. It bears far more resemblance to a Cold War-era border fortress than to a civilian transportation hub. Electrified double fences, perimeter infrared cameras, and patrols around the French terminals. This is a harsh response to new hybrid threats in attempts at physical intrusion. The reinforced concrete pipe itself, beneath the water surface, leads a separate life hidden from passengers. At night, when the flow of trains subsides, entire armies of engineers and flaw detectors descend there. They methodically replace cracked insulators, weld joints, and scan the concrete with ultrasound. It is an endless Sisyphean struggle against entropy, where one cannot pause even for a single day. Huge industrial fans on the banks relentlessly pump millions of cubic meters of fresh air into the depths. Cooling units work around the clock to cool the water in the pipes, preventing the tunnel from overheating to critical levels. The entire life support system runs at full capacity simply to maintain the physical status quo. The tunnel cannot exist autonomously. It is entirely dependent on an external energy supply. It has become a concrete monument to human stubbornness and our inability to back down in the face of losses. We once punched this gigantic hole in the Earth's crust, and now we are bound to maintain it forever. Any failure in this ultra-complex electronic chain threatens the immediate collapse of the entire infrastructure. It is a triumph of engineering that has turned into a lifelong dependence on our own technology. Formally, this is still the fastest and most technologically advanced route from London to Paris. Passengers still drink coffee, gazing out the black windows of the cars as they race through the darkness. But behind the train's thin exterior lies the intense work of thousands of sensors, pumps, and cables. In fact, it is 50 kilometers of absolute vulnerability to technical failure. The modern tunnel is a vivid lesson in the limits of scaling complex systems. The more functions we load onto this structure, the more fragile its foundation becomes. The attempt to subordinate geology to economist calculations was only half successful, requiring a compromise. Nature allows us to use this corridor as long as we pay the bills for its maintenance. The management company has long since accepted that there will be no victory in this war. The main task today is not to improve the tunnel, but to prevent it from deteriorating and collapsing. Every technical solution is aimed at preserving the current state, not at development. The project has frozen in a state of fragile, artificially maintained equilibrium. We've grown accustomed to viewing infrastructure as something fundamental and eternal, like the rocks themselves. But this tunnel proves the opposite. Large systems survive only through constant movement and ongoing maintenance. If the pumps are shut off for just a week, water and salt will destroy everything that has been built over decades. A time capsule that requires intervention every second to survive into the future. That is precisely why a trip under the English Channel will never be an ordinary event for those who understand its essence. It is a temporary truce between human pride and the indifferent pressure of the ocean's masses. Recall that gentle vibration of the cold glass in the cozy carriage of a high-speed train. Now you know for certain that it is not merely the acoustic noise of wheels rolling along the tracks. It is the sound of matter's ceaseless resistance to the colossal and hostile pressure of the ocean. It is the strain of a system operating at the very edge of its inherent physical capabilities. Over half a century, the island has shifted from the idea of security through isolation to chronic vulnerability through connection. The Eurotunnel was built to provide absolute freedom of movement for goods, but in return demanded strict control over space. It began as an ambitious commercial startup and became an overloaded and fragile geopolitical artery. Every technical solution implemented to save it from collapse only irreversibly complicated the structure. Control over space always comes at a steep, irreversible, and ever-increasing cost. The tunnel stands proudly and functions not because nature has finally surrendered and yielded to the engineers. It exists only because we pour energy, money, and labor into it every second without complaint. We have not conquered the English Channel. We have simply learned to survive uneasily within it. Form has triumphed over substance, turning a transportation route into a constant battle for survival. Major infrastructure projects are never truly completed. They merely enter a phase of perpetual repair. We keep these arches from collapsing because we have staked too much on them. One day, this underground bridge may become too costly for the unified economy, but as long as the pumps keep pumping water and the fans keep blowing air, trains will continue their journey in the darkness. The illusion of victory over the depths will be sold with every new ticket.